which is one of the most intimidating seeming equations that you're going to learn for the MCAT. But in the course of this lesson, we're going to take apart Bernoulli's law and examine each term individually and see what it teaches us about a fluid. Take a moment and read over this question stem right now, and then please continue. This question stem itself isn't so long, but the diagram that accompanies it might give you some hint as to how actually challenging this question is. And to help us simplify this question, I want to first make an analogy to another scenario that's a little bit easier to visualize. And that is a rock that is rolling down a hill, maybe through a little bit of a valley up to its final position. The question asks, in what ways is this scenario with the rock rolling down a hill similar to that more complicated fluid dynamics question? And I'll just tell you the answer right away. It's that they're both applications of conservation of energy. So my first real question for you, record in your lesson book, what does it mean to say that energy is conserved in a physics question? In this or any physics question, to say that energy is conserved is to say that the sum of all the different kinds of energy involved initially equals that same sum of all the types of energy finally. Now, in this question, we're trying to keep things simple. So we're going to look at how potential energy turns into kinetic energy and vice versa. But in a more complex physics question, like the fluid dynamics question that we're considering as well, we might see that other types of energy are going to be involved additionally. Let's consider this rock as it travels during the first segment of its journey, which you might consider from its initial point to a height that is going to be equal to its final height. That height's going to be really special for reasons that we see in just a minute. But before we get there, I want to think about the rock in its initial position. Initially, this rock has the greatest potential energy it will ever have at any point in this entire question. Take a moment and think about why the rock's potential energy initially is also its maximum potential energy. Potential energy can be computed on Earth as mgh, and because the rock's initial height is its highest height, its initial potential energy must be its maximum potential energy. And if that was your reasoning, you are exactly correct. But there's another way of explaining the rock's initial potential energy that uses conservation of energy. Because the rock is just sitting at the top of the hill initially, its kinetic energy must be zero. And that means that initially the rock's energy is all potential energy. Because the rock has to share its energy between potential energy and kinetic energy, well, if it doesn't have any kinetic energy to begin with, then its potential energy must be the maximum it ever will be. And so as the rock starts to roll down the hill, we're going to see that it begins to pick up speed so that potential energy begins to go down from its maximum and kinetic energy begins to increase. Now, there's a reason that I want to focus in on this particular height. That is the position where the ball's height is equal to its final height. And the reason why is that at this exact point, as the rock rolls down the hill, its kinetic energy is going to be exactly equal to its final kinetic energy. Take a moment and justify for yourself, using conservation of energy or any other explanation that you can think of, why the rock's kinetic energy at this position is going to be equal to its final kinetic energy. Because the rock is at the same height as its final position, it must have the same potential energy as in its final position. And the rock's total energy at all points is constant. So if the rock's total energy right now is equal to its final total energy, and if the rock's potential energy right now is equal to its final potential energy, its kinetic energy right now has to be equal to its final kinetic energy as well. But there's another way of thinking about this that's a little bit more qualitative. Our rock is going to continue rolling down the hill, and as it does that, into the bottom of that valley, it's going to continue to gain kinetic energy. But then on the other side of the valley, our rock begins to roll back up the hill, and it slows down. So you might consider that every joule of kinetic energy our rock gains on the way down the hill, it's going to give back up on its way to its final position. Here's the takeaway. From the perspective of conservation of energy, it's almost as if that valley never happened. In these kinds of problems, all we really care about is the initial energy and the final energy, and the path that our object takes to get from initial to final doesn't actually matter. Now, there's one more mathematical trick that we're going to employ in order to help us simplify this question even further. This is going to seem a little strange at first, but let's set h equals 0 at the final position. You might be tempted to set h equals 0 as the very bottom of the hill. And there are some advantages to doing that. For one, it's pretty easy conceptually to think about that height as being h equals 0. But there is another really big advantage to setting h equals 0 at the final position as it pertains to the final kinetic energy and the final potential energy. We can actually rule out one of these variables because of our decision to put h equals 0 as the final height. Go ahead and think, which of these variables can we rule out as a result of this decision? Because potential energy can be calculated as mgh by choosing the final height to be 0, we can say that the final potential energy is going to be 0. And this is a great simplification. The final kinetic energy must be equal to the initial potential energy. And the ultimate takeaway is that we can make this simplification. We can let the final height be h equals 0, because when it comes to conservation of energy problems, the only thing that matters are the initial energies and the final energies. Whatever weird stuff might happen in between doesn't end up influencing the final result. Now let's return a little bit more explicitly to fluid dynamics. We just learned about conservation of energy, which is a great mathematical tool for simplifying many physics questions. But when it comes to fluid dynamics specifically, another mathematical tool that you'll need on test day is Bernoulli's equation. Consider this term right here. That just looks so similar to kinetic energy, 1/2 mv squared. But it just isn't until you consider the definition of rho, which is density. What is density? Density is mass per volume. So if you break out that term density, what you find is literally 1/2 mv squared divided by volume on the bottom. That is to say, 1/2 rho v squared from Bernoulli's law is actually kinetic energy per unit volume. Using that trick, you might also consider rho gh. If you break out density and simplify this term into its two constituents, think about what you're going to get in that case. Rho gh simplifies down into mgh, which is gravitational potential energy per unit volume. So if you looked at those two terms and you initially thought about kinetic energy and potential energy respectively, great job. Your intuition is exactly correct. We'll talk about what the meaning of that per unit volume bit is in just a little bit. But first, let's focus in on how we can simplify pressure, because that seems to be the odd man out so far. First and foremost, think about what is the definition of pressure mathematically, and also what would be the units used to describe pressure. Pressure is going to be equal to force per unit area. This is another great formula to memorize for test day, but it makes a lot of sense qualitatively as well. If you imagine a bunch of water particles inside of, say, a water tank, those water particles are going to be constantly bumping into each other, and they're also going to be constantly bumping into the walls of that water tank. That is, these water particles are going to apply a net force to the walls of the water tank having surface area. So there you have the two terms. That's one way to think about pressure. The units for pressure are newtons and meters squared. I want to do another cool little mathematical trick that's going to give us another way to conceptualize pressure, a way that's actually a lot more useful when we consider Bernoulli's law. Let's multiply those units by meters on top and meters on bottom. Now, we're allowed to do this because meters over meters equals 1, and you can multiply anything by 1. And what that means is we end up with Newton meters on top, which are joules, and meters cubed on bottom. So here we have another situation where we have a type of energy on top and meters cubed, which is volume on bottom. Physicists sometimes refer to this definition of pressure as the energy density of a fluid. And so that pressure term itself can be broken down into a type of energy on top divided by volume on bottom. Taking all these ideas together, what we see is 3 different types of energy per volume on the left and 3 different types of energy per volume on the right. Bernoulli's law is literally another application of conservation of energy. We are almost ready to attack our water tank problem. There's just one more thing we have to understand about Bernoulli's law, and that is what that whole per unit volume business was all about. I want you to imagine a stream running down a mountain. If I were to ask you, what is the potential energy of the water in that stream? That question doesn't really make sense, right? Because the water at the top of the mountain clearly has a greater potential energy, and the water in the stream at the bottom of the mountain has a less potential energy. And then because the stream is continuous from top to bottom, you'd really expect a whole range of potential energies in between. To get around this difficulty, scientists instead focus in on a small volume of fluid as it flows through the system. This is often called a test volume. And they'll think about how those quantities of kinetic energy, potential energy, and pressure change as this fluid flows through the system. And that gets us right back to Bernoulli's law. We're going to think about how this test volume's kinetic energy, potential energy, and energy of hydrostatic pressure are initially, and how those things might change as we get to the final position. Let's now break down our small test volumes pathway through this system. During this first leg of the journey, what would you expect is going to happen to the potential energy per unit volume? As our test volume flows down through the water tank, the potential energy is going to go down, really for exactly the same reason that a rock rolling down a hill will lose potential energy. But now that we recognize Bernoulli's law as simply an expression of conservation of energy, what that means is that for this total sum of pressure plus kinetic energy per volume plus potential energy per volume, for that sum to stay constant, one of the other two terms must have to go up. And that will actually be the subject of our next prompt. So for right now, let's take a look at what happens next. From here, our small test volume is going to go down the pipe through that 300-meter segment that's not shown and back up to its original height. This certainly looks an awful lot like our rock rolling through that valley back up to its final height that we saw earlier. So let's apply the same trick that we used earlier. Let's let the final position's height equal 0. Record in your lesson book why. What's the advantage of doing that? This fluid dynamics problem certainly is a lot more complex than a rock rolling down a hill. But in the same way that we did earlier, by setting the final height equal to 0, we can eliminate that last variable entirely. In fact, again, because this is a computation of conservation of energy, all that really matters to us is the initial position and the final position. And what happens in that snake-like pipe segment doesn't actually matter to the computation at all. That's a huge simplification for us. Finally, because we are going to end up needing the initial potential energy, remember that because the height equals 0 is the final position, we want to consider the difference in height from initial position to final position to find the initial height. That difference in this question, given the numbers from the question stem, is 5 meters. Having knocked out the final potential energy variable, let's see if we can now eliminate another one of the variables from Bernoulli's equation. Specifically, we're going to see that the initial velocity of our fluid is essentially 0, which is going to allow us to knock out the initial kinetic energy term. And we'll do this using the continuity equation. The continuity equation is a great little equation that explains such things, for example, as why when you put your thumb over the end of a garden hose, you suddenly have a water weapon. I think it's helpful to break this equation down in terms of units. What we have for cross-sectional area is a unit of meters squared, and for velocity, we have units of meters per second. So what this says is that the meters cubed on the left per second has to be equal to the meters cubed per second on the right. The continuity equation basically says that the volume flow rate of fluid is continuous. How does that apply to this particular situation? The water tank has an enormous cross-sectional area relative to the cross-sectional area of the pipe at the bottom. So given this equality, think about what effect that should have on the velocity in the water tank compared to the velocity of the fluid in the pipe itself. Here, because the water tank's cross-sectional area is so very, very big compared to the outlet pipe at the bottom, What that implies is that the velocity must be very, very small on the left, and the velocity within the pipe must be very, very big on the right in order to keep this equation balanced. Again, this is a lot like putting your thumb over the end of a garden hose. By decreasing the cross-sectional area of that garden hose, you increase the velocity with which water comes out of that hose, and this is what allows you to spray down your friends or your pets. And in this case, because that water tank's cross-sectional area is so very big, the velocity of the fluid draining out of that is nearly zero. This is like a bathtub that is draining at an extremely slow rate. If you left it there all day to drain and came back, sure, you would notice a difference, but moment to moment, you essentially can't really see the water leaving. Lastly, let's solve the question. We were originally asked what the fluid's velocity is as it exits the pipe, and we now have all the tools and the tricks to be able to answer this quickly and efficiently. To begin with, let's review. We're able to rule out 1/2 rho v initial squared. Why? As we just saw, the fluid's velocity in the water tank is essentially zero because the cross-sectional area of the water tank is so big that the tank is draining at an extremely slow rate. So that knocks out our 1/2 rho v initial squared term. Taking a look at the right-hand side, we also saw that we can knock out rho gh final. Again, why? We were able to knock out the rho gh final term because of a little bit of mathematical trickery. Specifically, we get to decide what the final height is, and so we set the final height as equals to 0. The reason we were allowed to do that is that even though the water dips below that final height as it passes through the pipe, in conservation of energy questions, only the initial position and the final position matter. That whole 300-meter long pipe we could just treat as if it isn't there, and that allows us to knock out the final potential energy term in Bernoulli's law. There's one more simplification that we can do, and this one comes from the question stem. The question stem tells us that the top of the tank is vented so that the pressure inside the tank is 1 atmosphere. How does this allow us to eliminate both of the pressure variables in one fell swoop? Remember that our pipe opens up to the air. That means that the fluid, just as it exits the pipe, is also experiencing 1 atmosphere of pressure. So we can eliminate Pi on the left and Pf on the right through simple subtraction. What that leaves us with is the rho gh term on the left and 1/2 rho v squared term on the right. Again, this is so similar to our rock rolling down the hill, because remember, for that question, we had an initial amount of gravitational potential energy and a final amount of kinetic energy. Go ahead and solve for final velocity from here. Be sure to reference the question stem for any numbers that you might need to plug into this equation. First, knock out the density term on the left and right, and what that leaves us with is that 1/2 v squared on the right equals 10 meters per second squared, which is always a good approximation to use for gravity on the MCAT, times the height that the water started above the final position, which was 5 meters. Doing a little bit of solving from there, we multiply both sides by 2 so that V final is 10 meters per second. In this lesson, you saw that Bernoulli's law is really just a statement of conservation of energy, specifically for fluids. This is one of the most challenging topics that you're going to have to know for test